we'll have probably some more questions on the homework. We are going to move on, and we will post the P, and if we have more questions, we can talk about them. All right, so we move on today to finally conquer the question of how do we do this for arbitrary functions, right? Can we just come up with a power series always? Today you'll walk away with an answer to that question. Okay. So let's just consider the generic power series that we started with on day one. This is like every power series should be able to be written in this way, we said, right? This is what we mean. This is the definition of a power series, right? Something times x to the 0 plus something times x to the first, etc. Okay. And I want to ask, just like it came up in the warm-up, what is P0 for this generic function? Don't you just get C0, right? Great question. Love that question. What about P prime of x? Let's ask what P prime of x is first, and then I want to ask what's P prime of 0? What would P prime of x be? Well, the C0 goes away. If you're differentiating, keep in mind all the C's are just constants. So what do we get? Yeah, you get C1 plus 2C2 times x plus 3C3 x to the second, etc. And so what is P prime of 0? That is, if you plug 0 into the thing you just said, what do you get? Yeah, just C1, yes. Good. When we're talking derivatives of polynomials, we're like in a happy place. You're like, I know the power rule. Let's do it again. What's P double prime of x? You can look at this now and take the derivative of that. C1 goes away. What do we get? We just get 2C2 plus 6C3x plus 12C4x squared. And so what's P double prime of 0? Yeah, just this coefficient right here. 2C2. Very good. Guess what I'm going to ask next? I guess let's just get right to the point. What's P triple prime of 0? Yeah, 6C3, right? And in a minute, I'm going to ask what's in general P, the nth derivative of P, evaluated at 0. We want to like kind of notice a pattern going on here. Especially in light of the thing I told you that we're going to be able to do before we leave today, and that's come up with a power series for any function. There's something already afoot that you're noticing with the derivatives. If I come up with a power series for any function, don't I really mean just find all the C's? Right? Because if you know all the C's, you can figure out what all the C's are. If you have those in your hands, you have your power series. Right? Because the power series is just those C's times some x to x's to the various powers. So if you know all the coefficients, you've got the series. This already provides a little bit of an inroad. Is that okay? Okay. Into answering that question. So here are the results that we just established on the previous page. Again, let's make sure we understand. This is all general. This is for any power series at all. This is not specific to a particular function or a particular situation. So we found that C0, the very first constant, is just f of 0. So already do you understand that we're on our way to making a power series for a function, okay? You want to know the first term? Just plug in 0 to your function. How do you get the second term? That is C1 times x. What's C1? Well, if you have your function, take the derivative, you said, and plug in 0 to that. Isn't that what you said on the previous slide? Isn't that going to be C1? You said it, not me. That C1 is f prime of 0. See previous page. So we're making good progress, right? We have, if you want the power series, the linear approximation for the power series, it's just the function evaluated at 0 plus the derivative of the function evaluated at 0 times x. So far so good, right? We're making a power series here, you guys. For any function. by the way, if we stop there, what do we have? F of 0 plus f prime of 0 times x. What is that also known as? That's the tangent line at 0, isn't it? Isn't that f of 0 plus f prime of 0 times x? That's the tangent line at 0. It's also called the first order Taylor approximation, right? Now this one's a little trickier when we get to the C2, right? Because it wasn't true that it's just like the second derivative equals C2, right? That wasn't true. We actually had 2C2. That's okay. I know how to divide by 2. So if I know the second derivative evaluated at 0, I just need to divide that by 2, and I'll have C2. What about C3? Well, same thing. Now I'm writing this in an interesting way over here. Do you see what's happening to those coefficients? What happens when you peel down every power from n down to 1 and multiply by them? Yeah, so this is, it seemed like trivial. Why would I write that up here? But I wanted to start showing you the pattern here, that in general, what is Cn? Yeah, isn't Cn, no, if you do the thing we did on the last page, it seems like we keep getting this as our n derivative of our function. So, what's the Cn? It's just the nth derivative evaluated at 0 of our function divided by n factorial. And in general, so that gives us the coefficient, any coefficient we want. I just want to make sure this is sinking in right now, because like we said a minute ago, if we can lay hold of every one of our coefficients, Ci, right? If you have a formula for every coefficient, you also hold in your hands here the power series, don't you? If you name all the coefficients, then we're done. Just those things times x to the n, each one, right? This is a remarkable result. Did I give you enough time to let it sink in? A lot of notation there. Is that okay? You're okay with all the different? 0 factorial is 1. So here's the theorem more formally now. It's called, well, I won't say it's actually Taylor's theorem, but it's, so there's some preamble here, right? First of all, doesn't it, we've kind of been skating over this detail, but in order for a Taylor series to exist, obviously all those derivatives have to be defined. It has to be infinitely differentiable at a point, right? Most of our functions that we deal with that we like and we love and have grown up with are that kind of function, aren't they? When you think about all your polynomials are that way, all your functions, all your rational functions at places that aren't undefined are that way. Certainly all the trig functions, all your exponential functions. So this is not a huge demand that we have all these derivatives that we need. We finally have a purpose, by the way, for like the 8th derivative, or whatever. Suddenly we need lots of derivatives, not just the first 2. Sometimes someone will ask you to do the Maclaurin series expansion for a function. That just means around 0. They might also just say the Taylor series centered at 0. But notice how this is just slightly different than the last one. Why is it important that we be able to center our expansion other places and move to the right or left? Maybe you want to center it at 1 or something, or whatever else. One reason is, like, say you do a Taylor expansion for like 1 over x. Why can't you center that at 0? Well, right out of the gate, the function's not even defined, right? This first part doesn't even make sense, let alone the rest of that. So there are cases where if you want to do an expansion, you don't have the option of doing it around 0. Or it's possible that, because of the algebra of the situation, it's messy to do it at one place and less messy to do it at another place. So you have your choice if you're just, a lot of times we'll just tell you, do the expansion around 3 or something. So in general, we develop the theory at 0, but in general, we have at the center, right? So in general, this is the thing we want to kind of have down, this coefficient right here. It's
the nth derivative, this is like going to become like just part of your soul soon, right? What's the coefficient on x minus a to the n? This guy right here. The nth derivative of our function evaluated at the center, a, divided by n factorial. And if we truncate it, just like the warm-up today, if we truncate it at some place, n, we have a finite approximation of our function. It's probably a decent approximation, maybe, but we call that the Taylor polynomial order n. This is a big moment, too, because, like you said, this is just the tangent line right here, isn't it? I mean, this part right here is not unfamiliar at all. F of a plus f prime of a times x minus a, that's the linearization at a, isn't it? I hope that's like, just jumps off the page as being like one of your true loves. So what are we doing? What are we doing? We're just adding like, we're just adding a finer approximation of the function at that place. So that what happens at that place? Well, not just at a tangent line, what happens? Well, our tangent line agrees with the function at that value and its derivative, yeah? And both things match, the function value and its derivative. But now, as we go, not only does the function value and its derivative match there, but also the second derivative matches and the third. There's also some like profound philosophy at work here. Notice that the only thing we're doing with this function is evaluating it and all of its derivatives at one single point. And somehow we capture the whole function? How? If we only have information about one point. The reason I say that that's like philosophically deep is because you hear physicists say this too sometimes. If we know a particle's current position, velocity, acceleration, jerk, snap, crackle, pop, and all the other derivatives, if we know everything about all of its derivatives, we know its entire trajectory throughout all of time, right? Like, this is like a very deep idea, like that really bridges on like determinism in some sense, right? So this is like there's like philosophy on this slide too. Now, we have, questions about quantum mechanics and things too, but here's some guys with wigs. Just thought I'd show the picture of these two guys. So, there you go. You got a little history. Okay, I'll give you a few minutes to sketch that. They all look like Newton, kind of. Oh, no, he's got kind of like a bob, actually. Kind of like an up. Yeah, they all look like old European guys with long wigs. I had to saw this meme once, and I was like, my calculus students need to have that in their lives. So there you go. All right, back to your regularly scheduled power trees. Is this one we did, or it doesn't matter? But I don't know. This is certainly one you know how to do, yes, without the aid of this new theory. So let's do it both ways, though, and just we'll start with one that we know, and we can confirm using both methods here. This shouldn't take long to do. We'll do it both centered at 0 and -2. We'll do both. First of all, we'll just do it. Here we go. So at a for a, it's x equals 0 is what we're doing. Yeah. So what do we need according to Taylor's theorem? We need what? We need like a bunch of derivatives of this function, right? So we need f of x, and we need f of 0. What's f of 0? Yay. F prime of x. This sounds like not a lot of fun, but it's not too bad actually for this guy. You'll like it, right? What's the derivative of f prime? What's the derivative of f? Yeah, this was 6 times 1 minus x, so this is going to be, is it just that? To the -2nd? -6? Oh, wait. Chain rule, though, so I think this is right. Times the -1. So actually, this is going to come out really nice, isn't it? Okay. So this one's not a super interesting one here. What do we get next then? We get -12, oh wait, 12. Oh, we should be evaluating these too. I just got carried away. evaluate all these at 0, right? And then what? 36 times 1 minus x to the negative 4th. Are you tracking here with the chain rule happening with the negative 1 canceling out? Kind of nice, in fact. So I think we can keep going with this if you want. I think we're getting the idea. Okay. So what's f prime of 0? Sorry, my pen is failing again. F prime of 0. Okay. 6. And f double prime of 0. That is not good. 12. F triple prime of 0. Sorry. Positive 30. That's okay. Good. So what is the Taylor expansion? Are we ready to write it down? It's not like I said, it's not super interesting on this one. So how does it go though? It's 6. The first, it's f of x plus 6x over 1, over 1 factorial, times 12 over, I'll write it, 12 over 2 times x squared plus 36 over 3 factorial, right, etc. Yeah. Why are they what? Yeah, the chain rule throws out a negative each time. So I know. We picked a good first example that's like as easy as it possibly can be. Where in fact all the coefficients are just what? Which is what you expected before we started, isn't it? Using techniques from the last couple days, right? Isn't this just a geometric series? All right, so you feel free to write that in summation notation too, but I think we've made our point. So let's do it around around x equals negative 2. So at x equals negative 2, what would this expansion be like? Well, we still need these derivatives, but now we need like all of them evaluated at negative 2 instead. And the function itself too. So can we do that carefully? So here's the expansion at, I guess I should have just boxed that guy there. But, okay. At 0. Now let's write down the expansion at negative 2. It'll be, what's the first term? 6 over 1 minus negative 2, which is 2, plus, you plug negative 2 into this guy here. What do we get there? And the denominator will always have a 3 to some power, right? I think I'm seeing that already, right? So we'll have like 6. We'll worry about simplifying it later. 6/9, yeah. So 6 over 2 cubed times. Well, how do we write this? It's x plus 2 because that we're centered at negative 2, right? Again, if we stop there, that's just the tangent line at x equals negative 2, isn't it? That's all this is so far. But let's do another term here too. We're always going to get 6 over, it looks like, what's the next, or excuse me, now 12 over 27 times 2 though, right? Times x plus 2 squared. Plus some other things here. Right? Do you see where I got all these things? Let me make sure I'm clear about that. This is f double prime of negative 2. That is, I plugged it in here. And I got 12/27ths, didn't I? Divided by 2 factorial. That's how we get the coefficients in the Taylor expansion. Okay? So this is our first time doing it somewhere other than a 0. So I want to make sure you're clear on where all these numbers came from. So we have some simplification we can do. In fact, we always seem to be getting the 6 here again, don't we? Let's actually take the time to write what a general term would be for this then. Looks like it's always going to be what? 6 over, is it 6 over 3 to the n? that what it's going to be always? Times x plus 2 to the n. Does the first term work too? If you plug in 0 for n? Seems like the first term isn't. What's that? N plus 2. We need this to be n plus 2, and then it works? What? This one here? Let me think about it. I don't know if I go by that. I like the x plus 2 to the n, because that's, if we start at n equals 0, then that's what we get. I think I kind of liked that before. Maybe what I need is, I think I have an idea here. It's just geometric, isn't it? Let's see if we can fix that. What's the first term? I mean, really the common ratio is, can we say like the first term is 2/3 something? I mean, the first term is 2, but what are we going to multiply each time by? We should be able to think about this as a geometric. I mean, we're multiplying by like 1/3, which means, yeah, maybe we should say, 2 times 3 2/3 to the n. I want to make sure I said this right. 2/3 to the n. Here. I want to make sure it. Be 2 times. Yeah. Well, I didn't want to bring an n factorial in because it doesn't always cancel out up top here. Like we always get 6 over like some power of 3, right? Yeah, what are we multiplying by here? It looks like we multiplied by just 1/3, right? Every time? So is it just 2 times 1/3 to the n? Let's check that. N equals 0. Check that with n equals 1. Yeah. N equals 2. We get 2/9. Is that what this is? 2/9? Yeah, that's 2/9 if we simplify it, yeah.
Where does the x plus 2 come from?
It's centered at x equals -2.
But why doesn't it do the same with the x or 1 minus x? With the 0.
Yeah, it's still that. It's x minus 0. It's just we would just write x instead. So it's always x minus a. Sort of the center. Right. By the way, I have another way of getting. I think we got it here. I think that works, right? You just start plugging n equals 0, 1, 2 in, and you'll get, I think, what we have here. It makes me think, could I have rewritten this in such a way that reveals this geometric series instead? We didn't really touch on this the other day, but maybe there are like multiple ways to come up with these answers, right? I think maybe I can, right? Can I write this as, what would I have to do down in the bottom if I wanted an x plus 2 here? What would I have to put here? I'd have to have like a 3, yeah? Is that the same denominator? Okay. And then if I divide by 3 everywhere, top and bottom, I get 2 over 1 minus 1/3 x plus 2. Does that look familiar now? So we have another power series. We didn't really touch on this the other day, but this reveals a different form, and that's the one we just came up with too, right? So actually you wouldn't have to use today's theory to get either one of these if you really wanted to center it at -2, you could do it using our techniques from the other day too, and come up with two different power series. Now, I think the one we have here is a little better, just because its radius of its interval of convergence is a little larger, so I kind of like it better. Actually, I take that back. 1/3. No, this one is actually, it's centered at -2. We get an interval of convergence that's of size 6, don't we? So that's actually maybe better, right? Oh, I have another slide. Okay. Let's do one for another function that you know and love. Let's do sine x here. So this one I like because do you want to center it at 0? You can center it other places, but if we center it at 0, what do we get? I like taking derivative of sine x too, right? So f of 0, that's terrible. F of 0 is 0. F prime of x is cosine x, evaluated at 0 is 1. F double prime, not that interesting though, because it looks like every even ordered derivative, we're going to get 0, right? Is that what's going to happen? Taking the derivative again, we get what? Negative cosine. So there we get, for f triple prime is 0, -1. And now, repeat, yes? Okay. So I think we're back to sine now again. And we just keep getting 0, 1, 0, -1, 0, 1, 0, -1. So I think we're ready to write our power series for sine. Okay, first term is 0 plus 1 x plus 0 over 2 x squared minus 1 over 3 factorial x cubed plus, if we clean that up, what are we getting? We're getting all the odd powers, right? That's a factorial. Does that make sense? Right? So we get a nice pattern that emerges. It's just all these x to the n over n factorial, where n is odd, right? All right, you're well suited to explore any function now.